Okay, and our second
Okay.
speaker today will be Ryan Bushling. He'll be speaking about line segment extension via Kolmogorov complexity. Over to you.
All right. Yeah, thank you for the introduction. Thank you for having me. Uh, Pleasure to be here. I would thank you for moving the time an hour later than usual, but being no longer on the Pacific coast, uh, it's actually my nap time here. So I will try not to fall asleep and try not to put you to sleep. Okay, so this is based on joint work with Jake Fiedler of University of Wisconsin. And nominally, it's about the line segment extension problem. So if you have some union of line segments in Rn, and if you let L of E denote the lineal extension of this union of lines that I call E, union of line segments that I call E. So lineal extension is the union of the corresponding lines. So simple enough question, how does the dimension of the lineal extension of E compare to the dimension of the original set E? So that's the problem we're going to be talking about during this talk. A little breakdown of the structure. Some of these bullet points are going to have to be glossed over, but nothing essential. We'll start by contextualizing the main conjecture, Coletti's line segment extension conjecture, in this hierarchy of Kakea conjectures, or at least some small fragment of that hierarchy. The main results will be some packing dimension variants of these conjectures. We won't really talk about them again until the very end. The rest of the talk is going to be about the methodology. So Kolmogorov complexity and the point set principle of Lutz and Lutz. And what I really want to get at, sort of because I bound myself to this by submitting an abstract that I regret, is trying to get to the geometry of the point set principle and how that this sort of theorem of pure logic is manifesting itself geometrically in these lineal extension type problems. So we'll do a toy example and maybe talk a bit about these, what I call S-Hausdorff extensions. Everything in this section 3 is going to be a little bit simpler than the proofs of the main results. But then we can maybe get a sense of, okay, what actually would need to go into the proofs of those things. If we can do that, I'll be satisfied. Alrighty. So diving right on in, the Kakea conjecture, the generalized Kakea conjecture, and the line segment extension conjecture of Tomasz-Coletti. So the classical Kakea conjecture posits that if E is a Besakovich set in Rn, so it's a set that contains a unit line segment in every direction, then that set should have maximal dimension, Hausdorff dimension n. The generalized Kakea conjecture generalizes this if you don't have a line segment in every direction, but in some fractal set of directions, you instead have this inequality that the dimension of the direction set plus 1 is less than or equal to the dimension of the set E. And lastly, this line segment extension conjecture, if E is a union of line segments and L of E is its lineal extension, then the lineal extension has the same Hausdorff dimension as the original set E. So in the same paper in which Coletti posited this conjecture here, he did prove it in the planar case. The Kakea conjecture and the generalized Kakea conjecture in the plane have already been known for quite a while. What is the precise relationship between these things? Well, of course, the generalized Kakea conjecture implies the Kakea conjecture. Coletti showed that if the line segment extension conjecture is true in Rn, then the Kakea conjecture is almost true. Kakea sets have to have, or Besakovich sets have to have dimension at least n-1. And then conversely, Coletti and Andras Mate showed more recently that the Kakea conjecture implies the generalized Kakea conjecture. and that the generalized Kakea conjecture implies the line segment extension conjecture. So all three are almost equivalent. Line segment extension is just a little bit weaker. All right, so this is all in the packing dimension regime. When something's too easy or too hard, or if somebody has just already done the Hausdorff dimension version, do the packing dimension version. So that's where Jake and I went with this. So our two main results pertain to these conjectures in the plane. So first result, line segment extension conjecture for packing dimension in the plane. If E is a union of line segments in the plane, then the packing dimension of the lineal extension of E is equal to the packing dimension of E. And all right, in heavy air quotes, I'm going to say that as a corollary, we get this generalized Kakea inequality for packing dimension in the plane. So again, same statement as the generalized Kakea conjecture, but for packing dimension instead of Hausdorff dimension. The precise relationship is that in the course of the proof of this first theorem, this second result sort of pops out. It is not necessary to take this small diversion to get this result. So I would say that these two are more independent, but we've been running with this lie in order to keep cohesion in that paper that this is a corollary, and it's only a small untruth. I would like to know if there is an actual formal relationship between these conjectures in the packing dimension regime. I really don't know of one, a relationship between LSE, Kakea, and generalized Kakea. Okay, so second part of the talk, should keep an eye on the time. Second part of the talk, getting into the methodology now. We use Kolmogorov complexity to prove these results, and I'm going to start from the beginning, but also go through it rather quickly, just trying to lay down terminology, notation, and just a little bit of motivation. As I said, I really want to sort of expose the geometry here rather than get bogged down in the technicalities. So to compute the dimension of a set, we think about coverings of the set, right? When we define Hausdorff dimension, we use coverings by arbitrary sets, but we know that it suffices to consider covering by open sets, covering by balls, coverings by dyadic cubes. These won't give you the, say, Hausdorff measure, but they'll give you the dimension. And then maybe the starting point of the effective methods, as they're called, is that it suffices to consider families that are computable with respect to an oracle. All right, so what exactly does that mean? Well, at least say a little bit about what it means. This point 4 sort of gets into the proof of this point to set principle, but it's really also somehow sums up the point to set principle. So let's just not put the cart before the horse and state this. So given a point x and Rn, we can identify it as a binary string just by thinking about, say, well, there's a natural encoding, I should say, of points as binary strings. If you want, you can think of it as a tuple of binary strings, that's fine. And you can feed these things into a Turing machines can spit them out. And so the Kolmogorov complexity of X to precision R relativized to an oracle A, ignore the oracle for a moment. This thing is going to be the minimum length of an input to a Turing machine that is required in order to output X to R bits of precision. So writing a computer program that spits out the first R bits of X, what is the shortest program that I can feed to a Turing machine and get that output? What does this oracle do? This oracle is sort of like an extra database that your Turing machine has access to for free. So it's a countable collection of finite strings of zeros and ones. And at any time during the computation, this Turing machine can refer to the database and see if it contains a certain entry, see if it contains a certain string. And so having access to all these strings helps with the computation. It sort of like gets to consult this oracle and ask it countably many questions for free. The use of this for us is this point-to-set principle that we can use Turing machines and oracles and Kolmogorov complexity to compute the Hausdorff and packing dimensions of a set. So how do we do this? For every set X in Rn, the Hausdorff dimension of X is what here? So it's the minimum over all oracles over of the supremum over all points X in X of this quantity dim A of X. And what's that? That's the effective Hausdorff dimension of X relative to A. And that's just the lower asymptotic Kolmogorov complexity of X. So it's the lower asymptotic complexity. So Hausdorff dimension of X is the minimum over all oracles of the supremum over all points of the asymptotic complexity of X. And whether you take the lower or upper asymptotic complexity gives you Hausdorff or packing dimension, respectively. So I'm going to keep this theorem on the next slide and just state mantras that I like to keep in mind, two heuristics, motivating principles. So to compute the dimension of X, you want to find an oracle that minimizes the complexity of the most complex point of X. That's the point-to-set principle in a sentence. This doesn't really tie back well to the other ways of characterizing dimension that we know. And so the one that I've sort of settled on, and I don't know how legitimate it is, but the one that I've sort of settled on is the idea that the dimension of a set is the number of parameters required to uniquely describe or identify a point in a set. So on a curve, you need a single parameter to say where you are in a curve. If you're on a surface, you need two parameters to say where you are. We use basic properties of, say, curves and surfaces when trying to generalize these integer dimensions to fractal dimensions. So let's maybe start with this characterization, see what we can do from there. So, by this sort of logic, okay, it should take one parameter rather than maybe the expected 4 parameters. That's 4, not 4 factorial, but it also does not take 4 factorial parameters. It only takes one parameter to specify a point on the 4-pointer Cantor set, which may be surprising because at each step of the construction, you have to choose one of the 4 corners. So as you're trying to zero in on a single point of your Cantor set, you keep having to make choices in batches of 4. But at each time, you're also increasing the level of precision of your approximation of a point by a factor of 4. So you have 4 choices at each step, but you also have get a factor of 4 of better approximation of a point. So it's in that sense, this sort of sense of efficiency of your parameters that this is telling us that we only need one parameter to identify a point in the 4-pointer Cantor set. And of course, the big leap, if we use our imaginations, somehow it can take a non-integer number of parameters to specify a point in a set. Alrighty. So now we're getting into the proofs. And so, as I said, we're not going to actually attempt, well, I attempted to compress the proof of main results, but it was too complex. So instead I have a couple of smaller results that contain a lot of the same ideas. And my hope is that by the end of them, with just a brief word, I can give some sense of how the ideas from each of these proofs combine to give the proof of the main results. So let's try to prove this statement. A non-doubling bound for the packing dimension of lineal extensions. So if E is a union of line segments in Rn, then the packing dimension of its lineal extension is less than or equal to twice the packing dimension of the original set minus 1. And this is, I think, going to leverage the idea of number of parameters. What we're going to do is take the number of parameters required to compute a point of E and just take those parameters, feed them into an algorithm with some complexity, and that will output points of L of E. And what is that algorithm? It's simple. It's taking linear combinations. So the 2 is coming from taking 2 points of E. So let's start with a certain oracle that witnesses both the Hausdorff and packing dimension of E. So that's that oracle that obtains the minimum in the point to set principle. You can find an oracle that does both. A priori, you can only find one that does the Hausdorff or the packing dimension, but they're just databases. You can combine a countable database and a countable database to get a new countable database. So let's start with one of those oracles that witnesses the Hausdorff dimension of both the Hausdorff and packing dimension of E. Let's take any point on the lineal extension of E. So that's some point Z lying on some line L. We can compute that point, write it as Tx plus 1 minus Ty, where X and Y are points of E intersect L, the original set E, but on that same line. All right, and this also holds in a more quantitative sense. If X and Y are some fixed distance apart, which we are taking them to be, then if we know X, Y, and T, each to R bits of precision, maybe we know R binary digits of each, well, then we can basically get Z to R binary digits as well. There's very little error incurred in performing this linear combination. So the complexity of Z to R bits of precision is less than or equal to the complexity of X plus the complexity of Y plus the complexity of T plus the complexity of the operation of combining these things as a linear combination. Addition, multiplication, these are very simple operations. If you were to write a Python program to do these things, it would be rather short. And likewise, for a Turing machine, it would still be rather short. At most, big O of log R bits. But okay, so let's back up just one moment, pause just one moment. So if we divided by R right now, divide by R, R, took lim sups, we'd get that the packing dimension of Z is less than or equal to the packing dimension of X, packing dimension of Y, packing dimension of T. T is just a real number, so it has packing dimension at most 1, effective packing dimension at most 1. So we'd get dimension of Z less than or equal to the sum of dimensions of 2 points in the original set E plus 1. So what we get out is an upper bound of 2 times the dimension of E plus 1 rather than minus 1. But the trick is to reduce this from a plus 1 to a minus 1. We have 2 degrees of freedom that we haven't used yet. So the first degree of freedom is in choosing T. We can, since X and Y live on some line segments, we can move them relative to each other. And in particular, we can move them in such a way that T is, say, a rational number. So a rational number has a constant length description, requires maybe 10,000 bits to describe, and that's it. It doesn't increase with R. And so we can actually take this thing to have packing dimension 0, effective packing dimension 0. That would reduce this, that would get rid of the plus 1 that we had here. And we'd get an upper bound of 2 times the dimension of E, but we haven't got that minus 1 yet. What's the other degree of freedom we have? Well, we also get to slide X and Y, that pair, along this line segment. We can wiggle it a little bit. And we can do that in such a way, in fact, that the effective packing dimension of X is no greater than the supremal possible value of the effective packing dimension of a point on this line segment minus 1. So we can actually guarantee that because we have this 1 degree of freedom from sliding around, that we can also find a point that has one bit of saving. That's 1 degree less complex than a typical point. I put these in red quotes because this isn't exactly what we prove, and I'm actually not sure how to prove these 2 things in quotes here, but I'm also confident they're true. In any case, it's not quite what we prove. What we prove is a little bit more complicated, but also a little bit weaker. All right, taking this for granted, so we now have complexity of Z is less than or equal to Well, complexity of x is bounded by complexity of x prime minus r. Complexity of y, this complexity of t plus O of log r just turned into a little o of r. All right, now we divide by r, take lim sups, and the point-to-set principle gives us what we wanted. So that's how I'm trying to use this idea of number of parameters required to compute a point in the set. All right, let's see. I have until 15 after, is that right? I think so, okay. Alrighty, so next point of order is to briefly talk about this result of Neil Lutz and Don Stull. It's a difficult result, and I wish I understood it myself better. But if we can just sort of get a sense of what it's saying and the geometry of it again, that'll be enough to prove this next sort of toy result. And once we have this second toy result, I think we more or less have all the elements of the proofs of the main results. So one new idea that we need is the idea of encoding a point as an oracle. So a point is an infinite binary string. Granted, an oracle is made up of finite binary strings, but okay, I can write y as, a sequence of data entries. So I can always encode stick y in this countable database. I can always encode it in the database somehow. And so kry of x would mean computing x to r bits of precision, given that I have full knowledge of y. I can always access the database and get any digit of y I want for free without having to do any work. All right, with that notion in hand, well, I'll mention that certainly having y would have made our life easier back here, right? If we were computing z with full knowledge of x and y, that would have made things very easy. We don't often have this full access, but hypothetically, let's say we do have, we are computing one thing with full access to certain other parameters. So what Lutz and Stull proved is these circumstances under which the most efficient way to compute a point x comma ax plus b is by computing x and then computing a and then computing b. Normally, that's going to be an inefficient way to go about this. For starters, that's 3 things, whereas x comma ax plus b is 2 things. So normally, that's not going to be the most efficient way to go about it. But they prove this inequality that somehow says that this is actually the most efficient way to go about it if you're working with a not too large family of lines. So the precise statement, if little a and b are parameters, big A is an oracle, and x is any real number, then the effective Hausdorff dimension of x comma ax plus b is greater than or equal to the effective dimension of x relativized to a and b, plus the minimum of 2 values. The first value is the effective dimension of the parameters, and the second is the, again, the same quantity, the effective dimension of x relativized to a and b. And so you can sort of see what I was trying to summarize in this sentence here. The x comma ax plus b is at least as complex as, say, x and ab when ab is small. And so ab is small when we're working with a small family of lines. Then enumerating all the lines in our family is not a difficult task. So that's sort of what this inequality is saying. One point that sort of validates this interpretation is that the authors use this to prove the t less than or equal to s case of the ST Furstenberg set conjecture. There's only one other thing that I'd really like to say briefly about this. So I'll leave this on here for the recording. But I just want to get to this first idea that the oracle A represents context. So this, pardon me, this inequality has nothing to do with geometry. but A, I like to interpret as a context. It's a database that contains all these data entries. And maybe I got these data entries by consulting my psychic and asking for my lucky numbers, and she gave me this database. But that's sort of beside the point. Wherever this database came from, I can always feed it to an algorithm that interprets that data as geometric data. So although in some sense this is a statement of pure logic or of complexity theory to the extent that that abuts pure logic, it can always be recast as a purely geometric statement just by taking A to be a sort of geometric database, a database with geometric information. So that's where the family of lines is coming from. A is maybe saying something about families of lines, a certain specific family of lines, and a specific collection of points may be contained in those lines. That's sort of the right context, and we can find we can find a computer program of some fixed length that interprets the data in that way for us. All right. We have just a few minutes left. So I'll briefly state this other result here. Just say a couple words about how we use this Lutz-Stull inequality to prove it, and then maybe in 2 sentences say how we combine the ideas from our previous little proposition, the proof of this proposition, and how mixing together some of those ideas can get us the proof of the main results. So little generalization of lineal extension is this idea of an S-Hausdorff extension. So we'll say that if E is a union of S-Hausdorff dimensional subsets of lines for some S greater than 0, well, LS of E, the S-Hausdorff extension, is just going to be the union of the corresponding lines. And this result is that the Hausdorff dimension of this S-Hausdorff extension is less than or equal to the dimension of E plus 2 minus 2S. So this generalizes the line segment extension conjecture in the plane. Right, when S is equal to 1, this right-hand side is just the dimension of E. Okay, and so to prove this, we're going to use the Lutz-Stull inequality here. And let me see how I'd like to go about this. I think first let's just effectivize what we want to prove. So recast it in this effective language. So by the point to set principle, it's equivalent to show this inequality here, taking the minimum of the supremum of the complexities of all points. That's how we compute the dimension of a set. So we have that on this side, we have that on this side, and then our plus 2 minus 2s. All right, I can chop off this minimum on both sides and chop off the supremum over all lines on both sides and get this stronger statement that on every line L and for every oracle A, this inequality holds. And so it's that stronger statement that we actually prove. We're going to put an, let's see, how to phrase. We're going to put an upper bound and a lower bound on the dimension of a point Z in E intersect L. Is that how I want to say it? Let's roll with that. So let's take a point Z on E intersect L. I'll write that as x comma ax plus b. Then the complexity of that point, using the same reasoning as before. The idea that if we know x, a, and b, we can recover the point x comma ax plus b just by using basic arithmetic. We can bound the complexity of this ordered pair by the complexity of the parameters a and b and this r that comes from the complexity of x. All right, from that inequality, which I just reproduced here, divide by r, take lim inf, and you get this inequality for the pointwise dimension of Z. So that one was very simple. Then you want to prove a lower bound on the dimension of z, assuming that z is in also in E. I believe I misspoke. I said that z was in E intersect L. That last bound works. This reasoning works if z is just any point on L. Now we specialize to when z is a point on E intersect L. And the idea is that we can use the Lutz-Stull inequality on large points. We look at points with large complexity on that intersection of E and L. We apply the Lutz-Stull inequality, and we sort of get, or we do get a lower bound on the dimension of points on E intersect L. And so if you combined the lower bound of the dimension here and the upper bound of the dimension of arbitrary points on the line there, subtract one inequality from the other, and you get exactly the bound that you'd like. You'd get this difference between minimum of stuff and this thing, and if you parse out which value of the minimum gives you the larger value, a 2 minus 2s pops out. And then in the usual way, write these supremum over dimensions of individual points as the dimensions of sets. All right, very last slide. If we could, we would prove, we would take this exact same idea and use that to take the Lutz-Stull inequality and prove these two things. Unfortunately, the packing dimension version is not true. So if you were to just replace effective Hausdorff dimension with effective packing dimension, that statement isn't true. If it were true, you could use almost the same proof to get this first theorem here. Instead, you have to do sort of a multi-scale version. So for very special oracles, very special points at very special scales, you can get something that vaguely resembles the Lutz-Stull inequality. And basically that is how one does it. So you're going to use the same parameter ideas from the first theorem's proof, and this idea of using the Lutz-Stull inequality from the second theorem's proof, but work with a lot more annoying nuisances and a sort of multi-scale analysis to make it all work out. Okay, sorry for going a little over time. I'll stop there.